So, good afternoon, everybody. We will start our next session. The first speaker is I.Logashenko from Budker Institute, Novosibirsk. Measurement of muon G-2 at Fermilab. Please.
Thank you. It's a great pleasure for me to present the recent result from G-2 collaboration. I will start right from the end, from the result itself. Here is the new measurement of anomalous magnetic moment of muon. It was announced on August 10 this year. The precision is about 2 times better than the previous one, and now the world average is basically equal to the new precision, and the precision reached to about 200 ppb, parts per billion. That measurement is done in Fermilab by muon G-2 collaboration. That's international collaboration with mostly it's American, with very large Italian and British contribution and some contribution from other countries. And that's the experiment itself, 14-meter diameter ring, and yeah, there are people there. So now let me get to the details, some details and discussion of the measurement. So first, to remind what is measured, the gyromagnetic ratio connects spin and magnetic momentum. Dirac equation predicts that gyromagnetic ratio equal to 2 for point-like charged particle. Then, due to higher order corrections, there is an anomalous magnetic moment, which is difference from G from 2, relative difference. And the size of anomalous magnetic moment is about 10 to the minus 3. Since it rises due to higher order corrections, in these loop corrections, all possible interaction fields presented. So that makes an idea of experiment. If we compare, if we measure anomalous magnetic moment and compare it with theory prediction, we can check if there are extra contributions which are not described by the theory. So that's, in a sense, search for new physics. The precision is very important here because the massive fields give smaller and smaller contribution to the AMU. And just as an example, this contribution from strong interaction is 10,000 smaller than the electrodynamics, and weak is million times smaller. And the last point, it's the muon is the most interesting particle for which the anomalous magnetic moment can be measured in terms of the search for new physics, because for heavy fields, there is natural scaling which increases the contribution from heavy fields to anomalous magnetic moment by ratio of mass squared, so about 40,000 times. The new result from Fermilab is a last chapter, not the final chapter, the last at the moment chapter of a very long path worldwide effort to measure AMU. And it started actually more than 60 years ago. Let me just briefly remind the major experiments. Here is theory as we know it today. Here I will show the precision of experiment at particular point, and here what's shown is where the contribution of particular interactions, electrodynamics, strong and weak, is seen in this long number. So there was a series of CERN experiments famous with improving precision. You see the number of numbers increases. And precision increases. And the last CERN experiment was CERN-3, which is a very important experiment. It established the method how we measure anomalous magnetic moment up to date. Then, after a long period, the new experiment was done at Brookhaven, where the CERN-3 type experiment was done on the next level. And now it's done in Fermilab, where again the same method is perfected in a sense. And that's where we know And you see that the experimental precision is now 2 times better than the precision of theoretical expectation. And we deep into the weak contribution. So the precision we have now, it's about 20% of weak contribution. The basics of experiment. There are two. First, we need to measure, in order to measure anomalous magnetic moment, we need to measure the rate of precession of spin relative to momentum, not just precession of spin in the magnetic field, but relative to momentum. Because in this case, you directly reach measure A mu. So all experiments look the same. There is a storage ring where you store muons, you let them fly and in a uniform magnetic field and see how the spin precesses relative to momentum. The field is measured and the precession frequency is measured, and from these two numbers you can get anomalous magnetic moment. The second very important thing is technical. When you do that, you need to focus particles somehow. Usually it's done through non-uniform magnetic field, but that's very bad for this type of experiments. And it was realized that if you do this experiment with muons with particular momentum, 3.09 GeV, then the effect of electric field cancels out. So you can have electric fields in your device and they don't change your precession frequency. So now all experiments are done for muons of these 3 GeV muons that defines the scale of experiment, and the focus in which you need to store particle in the storage ring is done through electrostatic focusing. So that's the ring itself. 14-meter diameter magnet, very complicated structure with several thousand of knobs, which you can use to shim the field and make the field very uniform. And the field is measured in terms of the NMR frequency of proton. There is very complicated, sophisticated system for measuring the field and monitoring the field. The field map is measured every several days in a vacuum. There is a special trolley which goes and measures the field. Then during the measurement between these 2 points, the field is monitored by about 400 NMR probes just above and below the storage region. Continuously, and then there is a very, again, sophisticated system so that was relative measurement of the field, but to make it absolute, there are sophisticated absolute probes, which then all the probes in the ring are calibrated to the absolute probes, and overall we measure field to about 5×10⁻⁸. That's the precision of absolute field measurement. The muons now. The muons are generated the usual way. The proton beam here in Fermilab, it's from booster and then the recycle ring, and then this bunch of protons gets to the target. Pions from target, the pions with particular momentum about 3 GeV selected. Then these pions go into long delay line here and do 3 turns in what used to be antiproton accumulator in Tevatron era, and now it's a muon decay line. And all pions decay during this time, and we select the muons which go forward in the rest frame of the pion. This way you get very polarized muon beam. Then these muons are injected in the ring. Let me skip this part. In order to put them, so when injected, we need to put them on standard orbit, and for that there is a special very fast magnet which in 1 turn 150 nanosecond for 1 turn reduces a little bit magnetic field here, so the muons after they injected they put on a circular orbit in a storage ring. Electrostatic quadrupoles placed in 4 places are used to focus beam. And in order to see the precession of this spin, we use the properties of the decay of muon. So we measure, we detect positrons which are product of muon decay. For that, there are 24 calorimeters on inner side of the ring. And the idea is that because of the parity violation, the energy of the positron correlates with the direction of the spin at the moment of the decay. So if we, the total number of positrons certainly doesn't depend on the location of the spin, but if we put a threshold and look on the high energy part of the spectrum, then the number of positrons will be modulated with the precession. It will depend on where the spin points at a particular point. So what we see is this kind of modulation with precession frequency, which we can measure from this kind of measurement. And the last very important detector in the ring, a new one, it wasn't present in Brookhaven, are trackers placed right in the inside the vacuum chamber, which into places which allow, before the electron goes to the calorimeter, to get a positron, to get the track of this positron and propagate it and reconstruct the position of the vertex of the muon at the moment of the decay. And that allows us to see the muon beam and to see all the dynamics in real time of the muon beam. The main well, in principle, analysis is very simple. Here is our wiggle plot. We fit it to the function which has a wiggle and exponential decay of muon. And in principle, you get the frequency this way. If you do that, actually, the chi-square is very bad. And if you look at the Fourier transform of the residuals, you see a lot of peaks, a lot of frequencies. All that are manifestation of the beam dynamics, what happens with the muon beam in the storage ring. So to get the frequency right, all this behavior should be understood, and that was done. That's actually a huge job. The full fit function is much more complicated, and it has about, depends on the type of the analysis, between 18 and 30 parameters, but all these parameters are very carefully studied, cross-checked by different methods. And when we do the full fit of our data, you see in the residuals, there are no spikes, anything. So, and the chi-square is perfect. And it's important to understand all these effects, beam dynamics effects, because they shift omega A by 1 to 2 ppm, depends on the parameters of the running conditions. This is what we measure, the precession frequency of the proton and precession frequency, NMR frequency of the proton, so magnetic field and precession frequency of the spin in the storage ring. But there are, in addition to what we measure, there are some corrections which need to be done. They are, again, carefully studied in a big analysis. The whole collaboration is about 200 people, and half of these people are studying particular things, corrections or algorithms and so on. And after applying corrections, we get the final ratio of two frequencies, and then having measured two frequencies, then we use number of non-physical constants to get A mu. So that's the real formula is there. These constants together are known to about 25 ppb, which should be compared to 200 ppb is a precision of how well we measure this. So right now it's okay, but for the next generation of experiments, it will be important to actually do improvement in this part as well. And all the corrections shown here amount to about 600 ppb, which is probably okay. Now, this announcement which collaboration did, that was on the basis on run 2-3 data, and 2 years ago ago, there was a first measurement which was based on run 1 data. So let me briefly show the comparison between these runs and this data. First of all, statistics. Run 2, 3 is 4.7 times larger than run 1. So statistical error gets down more than a factor of 2. Here are the systematics for comparison systematics between run 2 and run 1. Red are run 1 and blue run 2, 3. So you see there is improvement in many systematics just because we have more data, so we see many effects, and because some improvements in their data itself. I will show a couple things now, but actually the 99% of work was done in all of the corrections and precisions, which didn't change much because they're already done good. But two particular ones improved by significant factor of 5, and I will show this. They improved because they were done not very well in run 1. One first was due to running condition in run 1. There were bad resistors not found until the end of run, which led to that charging time for 2 plates for electrostatic quadrupoles were wrong. So the beam was moving and the frequency of beam oscillations were moving during the measurement, and that made significant corrections. Now for it, all that was replaced before run 2, and now the beam is much more stable during the measurement. And another one was connected in big improvement that was largest systematic for run 1, that electrostatic quadrupoles, they charge and discharge frequently, and because of that there are mechanical oscillations, and when the charge plate oscillates, it produces magnetic field, and this field need to be taken into account, and we didn't know much in run 1 about the size of the field. It was measured only in a couple places, but before run 2 it was very, very carefully studied, and now we know the size of the effect. And there were other improvements as well. So that's the final result. For run 2, 3, the result is still statistically dominated. The statistical precision is 200 ppb, and this total systematic is 70 ppb. So it's 3 times better than the statistics. And what's also very important, that the systematic which will reach 70 ppb is actually better than was proposed for experiment. We expected to get to 100 ppb. So that's actually incredible achievement. Experiment already collected much more data, 3 times more data, run 4, 5, 6, which is under analysis right now. It will take a couple of years. So we expect another factor of 2 improvement in precision. And let me spend a couple minutes on theory. So what about theory? That's a result, but remember the whole story of G-2 experiment is to compare it to the theory. Well, the standard model, there is standard model prediction for AMU, and there are contributions from all known fields. So, and you see the precision of experiment is 20 in these units. And you see that the contribution from electromagnetic and weak interactions are very well known, but much better than the experimental precision. But the contribution from strong interactions is actually known 2 times worse than what experiment now measures. The reason is that we cannot calculate this contribution directly, and we do it through dispersive approach, where it's calculated using another experimental data, the cross-section of hadron production in a plus or minus annihilation. So as in the precision determined by the knowledge of this data. The last compilation was done in 2020 by a large collaboration called G-2 Theory Initiative, worldwide collaboration, about 200 theorists and experimental physicists. And that's the kind of today's standard model prediction for G-2. So if we compare to this, it's more than 5 sigma away. So kind of very exciting and interesting. But since then, the two other results were appeared. One is first high precision lattice calculation, not based on a plus or minus data. And it disagrees with a dispersive approach. It's here. And just this spring, the new next generation A plus or minus data was published, was announced by CMD3 collaboration, which I participate in from Novosibirsk. It will be the topic of the next talk. And you see that if we use data, the new A plus minus data, then actually the standard model prediction agrees well with the experimental value. So at this moment, the standard model prediction is unclear. All that need to be sorted out, but there are a lot of ongoing efforts. First of all, there are results from the next generation E plus or minus experiments. CMD3 is the first. There will be another measurement from SND. CMD3 will have more results as well. There will be new results from B factories, also ongoing. There is a dedicated experiment at CERN muon, which will measure the hadronic contribution completely different way through electron muon scattering. And there is a huge program in progress in lattice calculation, and they will also produce more precise data. So all that it's going right now, and we certainly expect within few years, the situation with standard model prediction should be much more clear. These are my conclusions. So the anomalous magnetic moment is measured to 200 ppb. Systematic uncertainty actually surpasses the expectation we had for experiment. 3 times more data is available for another more precise measurement in a few years. And the status of standard model prediction is unclear at the moment, but there are a lot of efforts, and in coming years, we probably will know more precise data for standard model precision as well. Thank you.
Thank you very much to the speaker. I would say very nice, energetic report. Question, comments?
So thank you. Very nice presentation, and indeed this is the hot topic of today's fundamental physics. And you just recall me some early research that was done by myself and my group. You have shown an estimate of the loop corrections to G-2 of charged leptons. And this is one loop diagram in the very beginning. Yeah, and normally people, if not use the exact expression for this, they use this estimation that is proportional to the ratio of unknown mass to the lepton mass squared, but it depends on the type of the boson. And it was shown in my paper that if the scalar, pseudo-scalar particles, you should multiply this square by the logarithm. And it could be an order of magnitude difference. And this should be accounted not in your research, but for people who make these estimations for new physics and extract constraints on physics beyond the standard model using these discrepancies that you are discussing. Thank you.
Sure, you're absolutely
Next
correct.
question. Comments? So thank you very much to the speaker again. So our next speaker is Геннадий Федотович. Отчество я. Геннадий Федотовich from Budker Institute, also from Novosibirsk. The title of the presentation, Pion form factor measurement with CMD3 detector at the electron-positron collider VPP 2000. Please, 25 minutes. Keep in time, please.
Previous speaker reported very nice results obtained by German-2 collaboration and Fermilab. It is very interesting, it is very important to compare these results with theoretical calculation, which is uses the hadronic cross section in frame of standard model. Web 2000 collider covers energy range up to 2 GeV. In this energy range, there are more than 20 different hadronic cross sections. But among them, there are 4 very important: 2 pion channel, 3 pion channel, 4 pion channel, and also 5 meson decay intercounts. But the 2 pion channels gives the main contribution to the anomalous magnetic moment of muon about 73%. So it's very important to measure this value, this process with CMD3 detector. I will present in the talk about measurement of the pion cross-section below 1.2 GeV with CMD3 detector at electron-positron collider Web 2000. It is outlined of my talk. I will most part of my talk devoted to study systematic correction and also to particle identification. It's 2 parts very important in this analysis. Hadronic contribution to the value A mu is calculated using this expression, and you can see there is the value, the inverse dependence on the S squared. Due to this dependence, weighting energy range of Web 2000 makes a dominant contribution to the value of A mu and determines its uncertainty. This left pion reproduces the contribution from different channels, 2 pion, 3, 4, and count, and other. But more important, the right part of this pion, it representing the quadratic error comes from different channels. And also you can see that the 2 pion channel has the dominant contribution in the final error. 2 pion, the measurement 2 pion channel has a long history, more than 20 years. There is presented results of this measurement comes from presented from different collaboration, but most precision data were obtained in the previous experiment, CMD2 and SND, with energy scan and with Chloe detector and Babar using initial state radiation. In the light of the final precision of the final experiment, where 0.14 ppm relative reason should be obtained, it is necessary to have contribution, the accuracy of the hadronic contribution comparable with this value. Let me recollect that the total hadronic contribution to the anomalous magnetic moment is about 60 ppm. So in order to have comparable precision, necessary to measure hadronic cross-section with precision about 0.2%. It's a very difficult task, really. There is a view of the hole where we can see the collider Web 2000, also to detector SND spherical neutral detector, and CMD3 detector. I thought that the Web 2000 collider covers the energy range from this point to this, and we have special system in order to measure beam energy using the Compton backscattered laser light system with precision about 50 keV. It's very important for this measurement. And also the collider Web 2000 using new accelerated technique, round bits. It's with have a special focusing solenoid in front of every detector with a magnetic field about 13 Tesla, and the current luminosity has about this value, but the project, we practically reach the project luminosity. And as I said, we have two detectors which taking data on this collider. There is a CMD3 detector, general view. It's very important that we have drift chamber in the center of the detector. Also, we have colorimeter based on liquid xenon colorimeter, liquid xenon with the thickness about 5 radiation lengths, and also the second part of the colorimeter based on cesium iodide crystals with the thickness about 8 radiation lengths. And the both and cup, we have another colorimeter using BGO crystals. We have also the detector surrounded about muon range system with time resolution about 1 nanosecond in order to mark cosmic events and to mark cosmic events first of all. There is a history how we take the data on the with CMD3 detector. Really, what began with the 17th year, a new jets and facilities and booster gave a big improvement in luminosity. As a result, we saw increased luminosity by factor, at least by a factor of 10. And also in the low energy range was used a new technique, beam shaking. It's also allow us to collect luminosity with the factor by 4 at low energies. As a result, we collected about this one of the inverse, this one integrated luminosity, and for 2 Pion channel, we have analysis only this part collected at low energies. As a result, we have analysis about 34 billion Pion events, about this one for muon, and 44 billion events for Baba scattering at large angle. The basic idea to measure is the next. Events with 2 back-to-back tracks at large angle are selected. Selection criteria include cuts on the momentum, vertex position along the axis, average scattering angle, collinearity angles, and so on. This graph represents our event display where we can see 2 collinear tracks inside drift chamber and cluster in the liquid xenon colorimeter, which belong to tracks. There we use this kinematic condition in order to select these collinear events. All this, there are a lot of cuts, and all of them should be studied carefully in order to understand the systematic, final systematic. We have used two approach to select Pion and electron and muon. For it, we used two approach. One was based on momentum based, and another on energy deposition. This left plot represents the event distribution versus momentum for energy 250 MeV, and we can see clear three spot. It's represent pion and muon and this electron. But when energy of the beam increased, this spot began to overlap, and we can see only two spots. This represent babar scattering at large angle, and these events corresponding to muon and pion. The separation pion, muon, and electrons in final states is based on a likelihood minimization, two-dimensional of momentum of two particles, P plus versus P minus, or energy X plus, Y plus versus Y minus. This is likelihood, and where F eta is a probability density function for electron, muon, and pion. Momentum, in case of momentum-based separation, these PDFs are constructed as follows. Monte Carlo generator specters are convolved with detector response function, which include momentum resolution, Bremsstrahlung, pion decay, and so on. In the whole, there were used 36 free parameters in feet per each energy point. Another case, when we have used separation based on energy deposition, PDFs are described by a generating function from log Gauss trained on the real data by target electron cosmic units and use about 57 free parameters in feet. The ratio number of pion to electron, one was free parameters of this feed. Only for the ratio number of muon to electron also was fixed according to P.He, except for low energy, where we can separately determine the number of electrons. Cross-check of full Monte Carlo confirms consistency between both approach, between accuracy about 0.2% about raw energy. This plot represents how these events are distributed along for this energy, how the distribution versus momentum, and you can see for this energy we can extract events with electrons, muons, and pions. But you can see that the feed very well describe this experimental distribution. It is slide demonstrates the cross-check of two approaches. Really, we have three methods to determine number of pion divided on the number of electrons: momentum by energy deposition and angle distribution of these events in the drift chamber versus polar angle. This plot represents this ratio where we use two approaches, momentum and energy deposition, for three different seasons, and you can see that both approaches for different seasons has a good consistency between them, also inside 0.2%. This plot represents angular distribution electron, pion, also muon, and also we can see a bit 3 pion events that penetrate throughout selection criteria. If we sum the events inside this energy region, all physical runs, all collected luminosity in this energy region, and also fit this angular distribution, this plot represents this ratio, and also we can see that the experimental points jump up and down inside this accuracy. It means that we very correctly describe angular distribution for all collinear events. Very important part for angle systematic study for polar angle. This some source of the systematic for electron, muon, and pion is uncertainty of the fiducial volume, track polar angle in DC, beam energy spread, and so on. The cross-section for EMUP particles depends significantly on the range of the polar angle used in the event selection. This graph represents how the efficiency degraded versus selection cut on the theta polar angle. When we in our analysis we use polar angle from 1.1 radian. If we will take both more small angles, the inefficiency sharply increase. But inside this limits also we can see a bit difference between all the particles for EMUP. The plot represents if we will normalize the result of selection for different theta cuts. Also, we can see that the form factor, we can see the stable form factor about with this precision level. This plot represents how we take into account the correction with nuclear interaction, with the decay of all these particles versus energy. This slide represents how the efficiency, track finding efficiency, cluster finding efficiency versus energy. But let me show that the final efficiency for the trigger was better than a bit than this value. Also, we have studied systematic connected with radiative correction. We have used two Monte Carlo generator, one of them based on based to use the Monte Carlo generator with photon jet in collinear region where photon energy inside narrow cones along electron or positron, and another generator based on the Monte Carlo generator with the name Baba Yaga, which was developed for Cloya experiments. Both these approaches has a bit different systematic errors, but they were used both in order to understand the systematics, and it was established that when we used the energy deposition, the final result for Pion for factor value is we have consistency inside 0.1%. There was done also a bit another checks. We studied charge asymmetry in E plus E minus for E plus P minus. There is shown the measure of this effect, and there also shown the result of the Scalar cut. We can see the big difference, but this difference was explained in this work, was published where in this part was said the raw meson exchange, and these results allow us to describe our experimental data. Another check was done with the muon number. There is shown the energy, the ratio number of muon to electron versus energy, and also we can see how very high accuracy for this ratio. There is collected all systematics in our experiment, and we can see that the total systematic around rho peak is about 0.7 percent and about 0.8% at low energy and about 1.6% at high meson energy and higher. There is shown the Pion form factor in our experiment. There is first observation 5 decay into 2 Pion. And this part, we increase this part in order to better see this effect. And there is, we can see the results obtained in our detector and compare with the before measurements for this value. You can see our results for Pion for factor measurement, and it is clear see that our data has bigger values in average with respect to other detector. This slide represents the dependence our data versus initial state radiation, and also we can see that the data of other experiments has a more smaller values. This left part of this graph represents the connection with the direct energy scan experiment, and also we can see that CMDT2 data has a bit smaller values in this part. They is stable with parameter which were there we see the results of our calculation for AMU value. It's a previous results, it's the current our CMD results, and if we compare, if we calculate the contribution to the value of mu, it will be this, and based on the previous all measurements, the results will be here. And if we calculate the difference, it will be about, the difference will be about 5 sigma. It's too huge. If we will use only CMD3 data and now plus Benel results, the difference will be only this one. This corresponds about smaller than 1 sigma standard deviation. Agreement between AMU experiment and AMU standard now at the current and the standard model is the current level of precision goes with the BSM signal found at LHC at energies above 1 keV. Doing the test with higher precision will allow to go beyond LHC, but it will be possible if accuracy of the hadronic cross-section measurements will be significantly improved too. At the moment, hadronic attribution continues to be limiting factor, and inconsistency between different experiments gives the dominant in uncertainties. And now I come to my summary. Let me show the main part of this summary. At the current moment, the combined null and Benel results for anomalous magnetic moment of muon uncertainty demonstrate inconsistency between different experiments, which gives a dominant uncertainty in calculation of the hadronic contribution within the framework of the standard model. Some upgrade of CMD3 detector subsystem are planned, NCAP and barrel coordinate counters, new drift chamber, and so on. Many analyses with hadronic cross-section have been published, many others are in progress. It's my.
Thank you very much to the speaker. Question, please. Wait for microphone.
Of course, this result is very interesting. New experimental data for the form factor in this region of energy, that is, which is substituted in this region of energies, to my understanding, in the total integral, only this place, yes? And but then the question appears: was the origin of the difference of, say, SMD2 and SMD3 analysis, because you are measuring only this region of energies, the form factor, whether it is coming from reducing systematic uncertainty in this, or it is coming, say, from the extra measurement of the extra points, and you may detect, analyze, where is the difference between previous results of SMD and these results of SMD.
Question to whom?
To the members of the SMD collaboration, of course.
Do you understand?
But unfortunately, today we have not clear explanation why we have so different results with respect to the CMD and CMD3 data. I can tell only a short comments, but it will be my own opinion. There is the CMD3 detector is absolutely different detector with respect to CMD2. It has new drift chamber. It has new calorimeter in the barrel part, I mean liquid xenon calorimeter, and so on. Many other features of the detector now is much better than previous detector has. It's one hand. On the other hand, we now have a new collider, which has luminosity more than 10 times greater than previous machine. It, one turn, allows us to collect a huge statistic. It, in one turn, allows us to study in more detail all different systematics. Before, we haven't such a statistic in order to study it. So it may be a difference. Maybe it can, in part, explain this difference. Also, I can, for example, I can say the next. Except 2 pion channel at CMD2 detector, we also measure 3 pion channel around omega meson. And we improve mass, width, cross-section at the peak, but our cross-section at the peak was a bit smaller than in other results, about on 3–4%. Also, we have measured the channel with 4
So
pion channel.
we out of time.
So you mean that
There are some hints.
there are possibilities to consider in future to check the SMD3 results in this region of energies for this form factor, and also include possible new data to understand the possible difference, the reason of this difference.
I
Is it true?
propose you to
Yeah.
continue this discussion, coffee break, because our Korean colleague waiting for his report. So next talk. Thank you very much again. Thank you very much again. So next talk, it's Professor Shi-Ping He
Yeah, it's an online talk.
for theoretical physics from Pohang, Korea. But please.
Can you hear me?
Yeah.
Okay, I can share the screen. Can you see my
It's
screen
good.
now? Okay, wait a moment.
Maybe
Okay.
you share.
Wait a moment.
Wait. Okay, take your time.
Okay.
Excellent. Now you can start.
Okay. Good afternoon, everyone. It's a great pity that I can't attend this conference in person. Okay. The title of my presentation is Scalar leptoquark and vector-like quark extended models as the explanation of the muon G-2 anomaly. In this talk, 3 papers are involved, while it is mainly based on the 3rd paper. First, let me give a brief introduction to the muon G-2 anomaly. It was first reported by the BESIII experiment In 2021, the Fermi experiment data increased the deviation to 4.2 sigma. Recently, the Fermilab muon G-2 experiment released the new data, and the previous speaker have already given a talk on this. Well, here we will not include the new data. On one hand, it can be caused by the theoretical and the experimental uncertainties. On the other hand, it can be a signal of new physics. We are interested in the new physics interpretations. Now, let's consider the new physics contributions at one loop. The mediate can be a scalar or vector. For each mediate case, there are Fermi QED vertex diagram and the mediate QED vertex diagram. Then there are totally 4 independent Fermi diagrams. In any new physics models, the contributions can be just a linear combination of the 4 basic diagrams. Here we will focus on the scalar mediate case. The left diagram is proportional to the Fermi electric charge. The right diagram is proportional to the scalar electric charge. For each diagram, there are 2 parts of contributions. One part is the contribution without carrier enhancement. The other is the contribution with carrier enhancement, namely proportional to the new Fermi mass. Then there are totally 4 independent functions. They are labeled as RFLL, ISLL, IFLR, and ISLR. The upper script F means the Fermi QED vertex diagram. The upper script S means the scalar QED vertex diagram. The lower script LL means without carrier enhancement. The lower script Li means with carrier enhancement. In the new physics models, the scalar mediate mass can be lighter or heavy. For the heavy scalar mediate case, there can be 2 scenarios. In the first scenario, the muon mass equals the Fermi mass and they are much less than the scalar mediate mass. In this scenario, there is no carrier enhancement. In the second scenario, the muon mass is much less than the Fermi mass and the scalar mediate mass. In this scenario, there is carrier enhancement MF over M mu. Now let's do some numerical estimations. In the first scenario, it requires MS over 1 should be order 100 GeV. For GeV scale scalar mediate, Y is 0.01 order. For 100 GeV scalar, Y is order 1. For TeV scale scalar mediate, it is not favored because of the perturbative unitarity. In the second scenario, there is carrier enhancement. In fact, the carrier enhancement can be induced by a heavy lepton or a heavy quark. When the new Fermi mass reaches from GeV to 100 GeV, it requires MS over the square root of YR should be ordered TeV to 10 TeV. In this scenario, the TeV scalar mediate is viable. Now let's consider the lepton-quark extended models. There are 6 typical scalar lepton-quarks. The triplet S3 doublets R2 R2 tilt and the singlets SE1 tilt S1 S1 bar. Here F is the new quantum number, which equals 3 times baryon number plus lepton number. There are also 7 typical vector-like quarks. 2 days ago, Margarita Rambolo have given a talk on the singlets T and B. There are also doublets XTTB-B1 and triplets XTB-TB1. In the minimal scalar lepton quark extended models, there are only two representations, R2 and S1, which can lead to the carrier enhancement. In our previous paper, we studied the one lepton quark and one vector-like quark extended models with R-type quark carrier enhancement. In the R2 tilt plus B1 and the S1 tilt plus B1 models, there are pure down-type quark carrier enhancement. In this talk, we will discuss the two models. First of all, let's look at the Higgs-Yukawa interactions. This is the standard model down-type Yukawa interaction. This is the vector-like quark Yukawa interaction. This is the vector-like quark mass term. For simplicity, we only consider the mixing between third generation and heavy quark. The left-handed bottom mixing angle and the right-handed bottom mixing angle are not independent. In fact, the left-handed bottom mixing angle is surprised by the factor bottom mass over bottom partner mass. After rotating the bottom and the bottom partner, we can obtain the mass eigenstate Higgs-Yukawa interactions. Then let's look at the lepton quark Yukawa interactions. In the R2 tilt plus B1 model, there are two type interactions. The first type is right-handed lepton interaction. This is the left-handed lepton interaction. After expanding the two interactions, we can obtain the right-sided interaction. If we rotate the bottom and the bottom partner into mass eigenstate, we can also obtain the mass eigenstate lepton quark Yukawa interactions. In the S1 tilt plus B1 model, there are also two types of Yukawa interactions. This is the right-handed lepton interaction. This is the left-handed lepton interaction. Similarly, we can obtain the mass eigenstate lepton quark Yukawa interactions. In the two models, there are 5 new independent parameters: the lepton quark mass, the bottom partner mass, and the right-handed mixing angle, and the 2 lepton quark Yukawa couplings. For the bottom partner mass, the direct search of pair production requires it to be greater than 1.5 TeV. There are also constraints from electroweak precision observables. Conservatively speaking, we can choose the right-handed mixing angle to be less than 0.1. For the lepton quark mass, the direct search of pair production requires it to be greater than 1.7 TeV. Now let's consider the contributions to the muon G-2 in the R2 tilt plus B1 model. For the R2 tilt muon Y interaction, there is no carrier enhanced contribution. For the R2 tilt muon bottom and the R2 tilt muon bottom partner interactions, there are carrier enhanced contributions, namely the FLR part. If the right-handed mixing angle is not too small, say order 0.01 to order 0.1, the bottom partner carrier enhanced contribution is much less than the contribution without carrier enhancement. Because the bottom mass is much less than the bottom partner mass, the bottom partner carrier enhanced contribution is much greater than the bottom quark carrier enhanced contribution. Then it is dominated by the bottom partner carrier enhanced contribution. There is one subtlety seen here. The FLR function vanishes accidentally if the lepton quark mass equals the bottom partner mass. So to produce enough contribution, there should be some mass splitting between the lepton quark mass and the bottom partner mass. In the S1 tutor plus B1 model, for the R2 tutor, for the S1 tutor muon bottom and S1 tutor muon bottom partner interactions, there are also chirally enhanced contributions. Similarly, it is dominated by the bottom partner chirally enhanced contribution. In this page, we show the numerical results. Here we consider two benchmark points. In the first benchmark point, the lepton quark mass is greater than the bottom partner mass. In the second benchmark point, the lepton quark mass is less than the bottom partner mass. In this table, we fix the lepton quark mass to be 2 TeV and choose the bottom partner mass to be 1.5 and 2.5 TeV. In the R2 tutor plus B1 model, the real part of YR star should be positive if the lepton quark mass is greater than the bottom partner mass. The real part of YR star should be negative if the lepton quark mass is less than the bottom partner mass. In the S1 tutor plus B1 model, the real part of YR star is always negative. In these models, there can be new lepton quark and vector-like quark decay channels. In the R2 tutor plus B1 model, if the lepton quark mass is greater than the bottom partner mass, there are new lepton quark decay channels, muon bottom partner and muon Y. Then it will lead to the new lepton quark decay signature, muon B giant and Z Higgs W. If the lepton quark mass is less than the bottom partner mass, there are new vector-like quark decay channels. The new decay signature of bottom partner is muon plus, muon minus, and B giant. The new decay signature of Y is muon, missing energy, and B giant. Similarly, in the S1 tutor plus B1 model, there are also new lepton quark and new vector-like quark decay channels. To estimate which decay channel is important, here we impose 4 ratios. In the R2 tutor plus B1 model, if the lepton quark mass is greater than the bottom partner mass, we choose the upper left ratio. If the lepton quark mass is less than the bottom partner mass, we choose the lower left ratio. In the S1 tutor plus B1 model, if the lepton quark mass is greater than the bottom partner mass, we choose the upper right ratio. If the lepton quark mass is less than the bottom partner mass, we choose the lower right ratio. In the 4 plots, we show the contour plots of the 4 ratios. The colored region are allowed by muon G-2 at a 2 sigma confidence level. Here we take the log of the ratios. In the R2 tutor plus B1 model, if the lepton quark mass is greater than the bottom partner mass, we find that in this parameter space, the new lepton quark decay channel can become important. In the R2 tutor plus B1 model, if the lepton quark mass is less than the bottom partner mass, there are new vector-like quark decay channel. Well, we found that the new vector-like quark decay channel is smaller compared to the traditional decay channel if the right-handed mixing angle is 0.1. In the S1 tutor plus B1 model, if the lepton quark mass is greater than the bottom partner mass, there is new lepton quark decay channel. We find that in this parameter space, the new lepton quark decay channel can also become important. In the S1 tutor plus B1 model, if the bottom partner mass is greater than the lepton quark mass, the new vector-like quark decay channel is smaller compared to the traditional decay channel. for the right-handed mixing angle to be 0.1. For the lepton quark and the vector-like quark, there can be pair and single productions. For the pair production, the cross-section sensitively depends on the lepton quark and the vector-like quark masses. For the single production, they depend on the electroweak couplings. Because of time limits, the detailed collider phenomenology will not be discussed here. Then let's make a summary. First, we give a brief introduction to the muon G-2 anomaly. For the TeV scale scalar mediator, the carrier enhancement is required. In our previous paper, we studied the one lepton quark and one vector-like quark extended models with archetype quark carrier enhancement. Here we discussed the R2 tutor plus B1 and S1 tutor plus B1 models with pure down-type quark carrier enhancement. In these models, there can be new lepton quark and vector-like quark decay channels. In some parameter space, the new lepton quark decay channel can become important. For the right-handed mixing angle to be 0.1, the new vector-like quark decay channel is small compared to the traditional decay channel. While for smaller mixing angle, the vector-like quark decay channel can also become important. That's all of my presentation. Thank you, everyone.
Speaker, you are great. You are in time. Kamsa Hamnida. So,
you.
question to speaker. Comments, please.
Professor He, thank you very much for very dedicated analysis of some additional contributions to within the discrepancy between the present experimental and standard model parts of G-2. So I would like, and you mentioned were treating the light and heavy scalars, yeah, as it is indicated in this transparency in this slide. And I would like to direct your attention that many years ago, so in the beginning of 90s, in a series of my papers, I just calculate all these contributions for any value of scalar and pseudoscalar particle masses. So, and probably these exact equations, the four last equations were obtained in my papers in 1990 in Phys Let's B and some other. So I think that you used an exact expressions, analytical expressions of these integrals. Yeah, there is an analytical expression for any value of scalar particle contribution. So I would like to advise you to check whether you just use this or just there is a logarithmic term that should be also included. Well, thank you very much.
Thank you for your comments.
Sorry, do you have any answer?
I just thank the speaker for the comments.
Okay, other question, comments? If no, thank you again to the speaker. In Korea, it's 10 p.m., too late, not so loudly.
Okay.
So, our next speaker, Dr. H.Zhang from University of Science and Technology from China. The title of the presentation are value measurements in BESIII. Please, Doctor. You have 20 minutes.
Hello, everyone. Can you hear me?
Yeah, it's okay. You can start.
Okay. My name is H.Zhang from the University of Science and Technology of China. Thanks for giving me the chance to give a report about the measurements of the R value at the BESIII. The R value is defined as the ratio of the leading order production cross sections ratio of hydrogen and muon pairs in E+E- collisions, as shown in the following formula. Since the production cross-section ratio of the muon pairs in E+E- collisions can be calculated directly from the QED, as shown in the next formula, the measurement of the R value is equivalent to the measurement of the total cross-section of the hydronic production. The importance of the R value is that it can help us to test the standard model. The first importance of the R value is that it is the basic input parameter of the abnormal magnetic momentum of the muon, also called the G-2. The standard model predicts that the abnormal magnetic momentum of the lepton can be separated to the contributions of the QED interaction, the weak interaction, and the hydronic effects. For the contributions from the QED and weak interactions, they can be calculated precisely by the electroweak theory. But for the hydronic effects, which can be separated into the leading order hydronic vacuum polarization, next leading order hydronic vacuum polarization, and the light by light processes further. The hydronic effects dominates the uncertainty of the measurements of the G-2, especially the first leading order vacuum polarization, which can be calculated with an integration of the R value further, as shown in the next formula, which means that the precision of the measurement of the R value determines the precision of the measurement of the G-2. Recently, the new Fermilab results about the G-2 released, and the differences from the dispersive calculation given in 2020 goes to 5.0 sigma in the left figure with red and green color marked. Moreover, the latest QCD results about the G-2 is much closer to the latest direct measurement, with yellow point in the left figure. If using the recent CMD3 result of the pi plus pi minus channel, the dispersive calculation goes much closer to the direct measurement. Therefore, a lot needs to be further understood for us, and the measurement of the R value is still very important. The other importance of the R value is that it is also the basic input parameter of the running of the QED coupling constant. The standard model also predicts that the contribution to the running coupling constant consists of the contribution of the lepton and the quark. The contribution from the lepton can be calculated precisely using the perturbative theory, and the contribution from the top quark is rather small since the top quark is rather heavy. The most important contribution is from other 5 quarks, and it can also be described with an integration of the R value, as shown in the formula. Therefore, the precision of the R value also determines the precision of the measurement of the electromagnetic running coupling constant. The bottom figure and the tables shows the numerical result of the running coupling constant at Z pole, and we can find that the uncertainty of the hydron contribution dominates the uncertainty. The collider we used is called the BEPC2, short name for the Beijing electron-positron collider 2. The region of the beam regions is from 1.0 to 2.45 GeV, and the following figure is a bird view of the BEPC2. We can see the BESIII, the storage ring, and the linear accelerator from the figure. The detector we used is called the BESIII, short for the Beijing Spectrometer 3, and the following figure illustrates the inner structure of the detector. From the inner to the outer, the important part of the detector, including the MDC, short for the main drift chamber, the TOF, short for the time of the flight, the EMC, short for the electromagnetic calorimeter, and the superconductor magnet, and the muon counter. Now, the BESIII collaboration has about 600 members from 85 institutions in 17 countries. And this slide shows the formula we used to determine the R value in experiment. The symbol N, the first symbol refers to the numbers of the observed hadronic events, and the symbol of the NBKG refers to the number of the residual background events consisting of the Monte Carlo simulation, the QED background, and the beam-related contribution from the data. And the sigma mu mu refers to the leading order QED cross sections for the E plus E minus to muon plus muon minus. And the L int refers to the integrated luminosity measurement measured by the analyzing the Barber events and has 0.8% uncertainty. And the epsilon hadron refers to the detection efficiency of the hadronic events, which is the most crucial task for us in this measurement. And the epsilon trig refers to the trigger efficiency and is around 100%. The symbol 1 plus delta refers to the ISR correction factor. And we use two schemes, which is the Feynman diagram and the structural functions. The agreement is better than 1.4%. This slide shows the general analysis strategy of our measurement. Firstly, we use the unscanned data from 2.2.324 to 3.6710 GeV as the input data. Then we use the information from EMC to reject the Barber and digamma backgrounds. Next, we select the good charged and neutral tracks. According to the number of good charge tracks, we apply different methods. For the one pure events, which means that the events that has only one good charge event, we use it to tune the generator since they have large background. For the 2-pore and 3-pore events, we apply further selection card to get 2-pore and 3-pore hadronic events. And for the events that has more than 4 good charge tracks, we directly count it as the hadronic events. Finally, by summing up, we get total hadronic events. To simulate the signal events, we use the lambda law model. It is a self-consistent inclusive generator based on the jet set at low energies. And the kinematic quantities of the initial hadrons are sampled by the lambda area law. The right figure shows the hadronization procedure in E plus E minus annihilation. Also the procedure the Monte Carlo models simulated. The initial state radiation process implemented from mass of 2 pions to square root of S. The phenomenological parameter of the Monte Carlo model are tuned to the data, and the lambda area law model has been used in most previous R measurement. Moreover, we introduced another Monte Carlo models as an alternative generator for cross-check. The right figure shows the contribution to the total hadronic R measure below 1.937 GeV, and we found that many exclusive channel has experimental results. And to use as much experimental information as possible, we create the hybrid model. It is a hybrid of 3 Monte Carlo models, including the conjugacy, which simulated more than 50 channels with experimental data. Second is the Foncallo, simulate the other 10 exclusive channels, and we use lambda law model to simulate the remain unknown processes. We have drawn many checks on the Monte Carlo models. This slide shows the comparison of the effective energy spectrum of the 2 Monte Carlo models, lambda law and hybrid. The following effective energy spectrum after ISR at 3.4 GeV are shown in the following figure. The spectrum directly reflects the I star returned processes and both lambda low and hybrid models, which marked in red and blue in the figures simulated. We found that although use two different simulation schemes, we can still get good consistent spectrum, which is better than 1.4%. This slide shows the comparison between Monte Carlo and data in a few observables, including the number of the good charge tracks, the polar angle of the charge tracks, the number of the isolated cluster in 2-point events, and the ratio of the EMC deposited energy and the momentum. The first row is the lambda law model, and the second row is the hybrid model. We can find that the both lambda law and hybrid models give good consistency with the data. Finally, with great effort, we release the R-value measurement between 2.2324 to 3.6710 GeV, contains 40 energies in 2022, as shown in the following figure. The accuracy is better than 2.6% below 3.1 GeV and 3.0% above. In our result, we have the result. The cross section is systematically larger than the PQCD prediction, and the difference reaches to 2.7 sigma between 3.4 to 3.6 GeV. In the future, we can do more R-value measurement using the battery data. This work will use the data from 2.2324 to 3.6710 GeV, which has 14 R-scan data points and around 110 inverse p-bar luminosity. For further analysis, we can use the energy from 2.00 to 3.08 GeV, contains 21 R-scan data points and around total 550 inverse p-bar luminosity. And we can also use the data from 3.85 to 4.59 GeV and contains 104 R-scan data points and has total around 800 inverse p-bar luminosity. To sum up, we have large amounts of data available for the R-value measurement. Totally, there are 139 scan data points from 2.0 GeV to 4.59 GeV, with larger than 100,000 hadrons each. And we can, in the future, we can get high accuracy R-value measurements in continuum and open charm regions. Also, the BESIII collaboration has other works about the R-value measurements. Firstly, as shown in the left of the figure, in the worldwide measurement of the R-value, when the energy is above 2.0 GeV, the inclusive method is preferred, while when the energy is below the 2.0 GeV, the exclusive method is preferred. But the R-value measured by the inclusive and exclusive method near 2.0 GeV has some differences that cannot be covered by the uncertainty. It is interesting for us to check this transition region, and the BESIII collaboration are taking effort to measure the R-value at 2.0 GeV in inclusive way. Secondly, the BESIII already has large harmonic data sets, and we can use the ISR technique to measure the R-value. With the ISR technique, the R-value from the pi plus chi minus to continuum region can be accessed, and with great efficiency. And finally is the summary of my report. Firstly is we have firstly is that the high accuracy R-value measurements is very important to test the standard model, including the running coupling constant of the QED and the abnormal magnetic momentum of the muon, also named G-2. And the first set of the R-value measurement at BESIII already published in 2022. The energy region is from the 2.2324 GeV to 3.6710 GeV, and the accuracy of our result is better than 2.6% below 3.1 GeV and 3.0% above. And the third point is that there are many possibilities of the R-value measurement at the BESIII, including we can do the R-value measurement at a broader center of mass of energy region and with different approaches. And that's all my report. And thanks for your attention.
Thank you very much to the speaker. We have a question. Please wait for microphone.
Excuse me, how many terms are you taking into account in the perturbative QCD prediction when you are comparing with your experimental data and are claiming that in the definite region of square root from S, you see definite deviation from perturbative QCD prediction?
You mean that the problem about our result with the PQCD prediction?
No. It is written down. Second, systematically larger than
the
QCD prediction.
Yes.
The question is how many terms in the perturbative QCD prediction you are taking into account in the process of the comparison? Yeah.
How many terms?
Only leading order terms. Only 1/3 from square root from QF square multiplied by 1 plus alpha S divided by pi with the probably massive dependence plus
Microphone.
Did you take into account alpha S pi square contribution and alpha S pi third contribution in the third power, and even available at present alpha S divided by pi in the fourth order term?
Sorry, I'm not. I can't see the accurate number of how many terms we have considered. But
yes,
but
you are claiming deviation from the perturbative QCD prediction. Are you taking into account in the process of this comparison higher order available up to alpha S pi to the fourth order? Yes or not? Probably not.
Okay.
I cannot give you the accuracy answer. Maybe you can check in our paper. But what I want to say is that we have done many efforts to check this prediction, because that after we find that our result is systematically larger than the prediction, we have checked our model, our measurement, and also our prediction. I think that we have considered enough, including the terms including the next leading order, but I can't give you the accuracy answer. Maybe you can check in our paper.
Sorry, Dr. H.Zhang. I propose to you both to communicate later with electronic email and so on, because it's a very specific, maybe a discussion for others. Okay. Any other question, please? Wait for microphone. Wait second.
And have you planned to measure R value for lower energies?
You mean that this page?
Repeat question again, slowly.
Can you have your possibility to measure R value for low energy? I mean, lower than 2 GeV.
With that, we only have energy points lower to 2.0 GeV. Yeah, and we are measuring. We are working on the measurement of the R value at 2.0 GeV from 2.0 GeV. Exactly.
Okay, other question? Comments? Thank you again to the speaker.
Okay,
Now
thank you.
have a coffee break.